Welcome back to Physics Tutoring for Mods. This video will be going over the PDF, the hard PDF for kinematics and motion graphs, and which incorporates all the previous knowledge from the videos that I sent out. So make sure to look at those if you feel like you're not understanding something I'm going over. I'll be going, as usual, over only a few select questions. So make sure to, if you have any other questions about any other of these, then make sure to book a session with me on Mods. Let's get at it. And before we start, I'll be using g is equal to 9.81, not g is equal to 10. So if you use that, you might get a tad bit different answers, but that's fine, right? This is just what I'm used to. A car accelerates from rest at 3.2 meters per second squared for 6 seconds. Find the car's final velocity and the distance it travels. Okay, so final velocity is given by this equation. This is one of the equations, which is the only one that works, right? Because we have velocity initial, which is 0, because it accelerates from rest. We have acceleration, and we have time. Velocity final is equal to 0 plus 3.2 times 6. Velocity final is equal to, then if you use your calculator for that, 19.2 meters per second. But it also asks us for the distance it travels, okay? So let's find that out as well. We can use this equation for that. Delta x, or you might be more familiar with xf is equal to xi plus v initial t plus 1/2 at squared. But I'm just going to write it as delta x is equal to v0t, because xf minus xi is just delta x. You substitute in velocity initial is 0, so this entire term cancels out to 0. And 1/2 at squared is the only thing left. That's 1/2 times 3.2 times 6 squared is equal to delta x. So delta x should give you exactly 57.6 meters. So that's how you find the displacement and final velocity using the big 5 kinematic equations. Right, so now let me erase this so we have it's a bit more easy to see this. Let's go over reading velocity from a position time graph. The position time graph below shows an object moving in a straight line. Find the object's velocity using the slope of the graph. Well, you remember that the slope of a position time graph is what quantity? Velocity, right? Because it comes out to be meters per second. And there's a bunch of rules for velocity as well. The slope of velocity is acceleration. Area under velocity is position. And the area under acceleration is velocity. Right now, we're going to use slope of position as velocity. So we just pick any 2 points and find the slope. I'll pick this point, which is 1, 3, and this point, which is 0, 1. So the slope between these points would be 3 minus 1. That would be in meters, right? Because the y quantity is in meters. And then all of that over 1 minus 0 seconds. So 2 meters per second would be the slope of this line. Now let's try a free body diagram. The free body diagram below shows the forces acting on a 12 kg. You might not be able to see it. 12 kg crate being pushed across the floor. Find the net horizontal force, the resulting acceleration, and state whether the crate speeds up, slows down, or moves at constant velocity. So we need net force x, we need acceleration, and we need to say whether it speed up, slow down, or moves at constant velocity. Const vel. So let me scroll down so you have more space here. So if you remember from the equation, F is equal to ma, net force is equal to ma, then we can use that equation to calculate this acceleration here. So net force in the x direction is going to be what? We have 40 newtons to the right and 15 newtons to the left. So the total net force in the x direction is going to be 40 minus 15 newtons, or 25 newtons. Okay, so we have that. Acceleration is going to be, so we have net force x, right? And it's only going to accelerate in the x direction because the normal and the weight cancel out. So it's only going to accelerate in the x direction. So net force x is equal to net force total. 25 newtons is equal to mass times acceleration. So 12 kgs times A. A is equal to 25 newtons over 12 kgs, or approximately should be close to 2. Yeah, so 2.083 meter per second squared. And then it's going to the right, right? Because the applied force, the net force, 40 newtons, is in this direction. So if the net force and the acceleration are going to be in the same direction, that means it's going to obviously speed up, right? The applied force and the net force are in the same direction, so it's going to speed up. If the objects, if the applied force was in a different direction than the net force, then it would slow down. So we have a velocity time graph here, which we went over, right? And it shows a jogger running at 3 meters per second for 8 seconds, then traveling around and jogging at -2 meters per second for the next 5 seconds. Find the jogger's total displacement and total distance traveled. So we know displacement is just the area under the curve of a velocity versus time graph. So the area here is 8 seconds times 3 meters per second. This is the length here, and this is the width. So I just multiplied those to get the area of a rectangle, or 24 meters, positive 24 meters. This here is negative, so -2 meter per second, because it's under the graph, right? So -2 meter per second times 5 seconds. So -2 is a bit wrong, because if you're going behind the x-axis but you're still above the x-axis, it would still be positive. But for now, you can imagine it that way if it helps you. Okay, just imagine any area under the x-axis is negative. So this is going to be -10 meter per second times second, so just -10 meters. 24 meters minus 10 meters, 14 meters. That's our displacement, because you add the positive and the negative. You add the signed areas. Distance is just the absolute value of both. So absolute value of 24 meters, because the distance is just the total amount you travel. It doesn't care where you end up, just how much did you travel. Plus -10 meters absolute value is just 34 meters for distance. Okay? Next question. A driver traveling at 28 meters per second slams the brakes, decelerating at 6.5 meters per second squared. Find the distance needed to stop. If a pedestrian is standing 50 meters ahead, does the car stop in time? Okay, so let's go over it. Velocity initial will be 28 meters per second. Acceleration would be -6.5, because it's going the opposite direction as velocity. It's decelerating. Find the distance needed to stop. If a pedestrian is standing 50 meters ahead, does the car stop in time? Okay, so let's find the distance that makes the velocity 0, because when it stops, velocity f needs to be equal to 0, right? When it stops. So 0 is equal to 28 meter per second. Or instead of that, we could use the other kinematic equation, because this one will give us time and then we have to plug that in to get more, so it's a bit messy. We can use Vf squared, 0 squared, is equal to Vi squared, 28 meter per second squared, minus 6.5 times 2 times delta x. So you solve that equation, you should get, so on this side of the equation, on the left side, you get negative 7884 meters squared per second squared. You have to divide that by negative 6.5 times 2, and then you get your delta x. So let me go ahead and do that. Okay, delta x is approximately 60.31 meters. Okay, does the car stop in time? Well, you see how the pedestrian is standing 50 meters ahead. So unfortunately, since the car stops in 60.31 meters, the pedestrian might get hit. Okay, because the car needs to stop at 60.31. The pedestrian is standing over here. The car has to stop over here. So the pedestrian is going to get hit. Now let's look at problem 6. Another free body diagram. Okay. A 5 kg bot on a frictionless surface has a 20 Newton force applied horizontally. Find the bot's acceleration, then find how far it travels in 4 seconds, starting from rest. So in this case, 20 newtons. So as I said, right, the main purpose of this PDF is kinematics, but it does have some Newton's laws mixed in. But this is the more basic Newton's laws, like very, very basic Newton's laws. The other force PDFs will have more complex questions. So let's go over it. 20 newtons is the applied force. Normal and the weight cancel out, so 20 newtons is the net force, because there's no friction pulling it backward, right? Whoops, that net and it looks a bit different. 20 newtons is equal to 5 kgs times acceleration. Acceleration is equal to 4 meter per second squared. This is straight from Newton's second law, right? Net force is ma. And then find how far it travels in 4 seconds starting from rest. So that's why I incorporated this problem, because it does hold a bit of kinematics as well. How far does it travel in 4 meter per second squared? Okay, so it starts from rest. We know velocity initial is equal to 0. And then that means we could just use this equation, right? Delta x is equal to velocity initial times time plus 1/2 at squared. Velocity initial is 0, so this whole thing just cancels out. Delta x is equal to 1/2 4 meter per second squared times 16 seconds squared. Seconds squareds cancel out. You're left with 32 meters. So if you don't understand where I got the 16 seconds squared from, it's just 4 seconds squared, because time has to be squared. Okay, 32 meters. That's how far it travels. All right. We have a velocity time graph that shows an object's motion across 3 segments. Find the acceleration during each segment and state during which segment the object is slowing down. So the slope of a velocity time graph is acceleration, right? Which I went over in one of my videos. So let's find the slope at each one of these segments. That's what's going to give us the acceleration at each one of these segments. So we have 4, 10 here, and we have 0, 0. So acceleration, I'm going to say segment 1. So acceleration 1 is equal to 10 minus 0. So 10 minus 0 meter per second over 4 minus, so this is also 0, 0, right? 4 minus 0 seconds. Acceleration 1 is just 2.5 meter per second squared. And anytime you have a flat line, you know the slope is 0. So this would just be 0 meter per second squared. This you have to calculate again. 10 comma 0, 7 comma 10. So 0 minus 10 meter per second over 10 minus 7 seconds. This is negative 10 over 3 meter per second squared, which is approximately, so there's no approximate here because this is a continuing decimal, but I'm just going to say negative 3.33 meter per second squared. And since the object's velocity is positive, but the acceleration here is negative, you can see how the velocity initial velocity was pretty high at 10, but you see how it's going down here? That means it's slowing down in segment 3. So problem 8 is a basic vector decomposition. I won't be going over that. It's just cosine and sine. Okay. We have projectile motion from a horizontal launch here. Problem number 9. A ball is launched horizontally at 8 meter per second. So velocity x initial is 8 meter per second from a 2 meter tall table. So yeah, the table is up here at 2 meters. Find the time it takes to hit the ground and the horizontal distance it travels. Okay. So in order to do that, you obviously have to pull from one of the big 5 kinematic equations. Just which one? The time it takes to hit the ground and the horizontal distance it travels. You might be tempted to use one of the time equations or the range or time of flight, which I showed you. But remember, that only works when they both end and start at the same place, which doesn't happen here. So you're just going to have to use one of the big 5. So I know velocity final over here, or y final, sorry, has to be 0 meters. Y final is equal to y initial plus VIY initial t plus 1/2 minus 1/2 gt squared. So y final is equal to y initial is 2 and y final is 0. So let me actually erase that. VIY is 0, right? Because the projectile is launched horizontally at 8 meters per second. It doesn't have any vertical vector. That only happens once it accelerates because of gravity. So it doesn't have any vertical vector at the start. It's just launched horizontally. So velocity IY initial would just be 0 minus 1/2, 9.81 times t squared, which is what we want to find out, right? T squared. We want to find out the time it takes. So negative 2 is equal to negative 1/2, 9.81 t squared. So you multiply by negative 2 on both sides. 4 is equal to 9.81 t squared. T squared is equal to 9.4 divided by 9.81. And t is equal to square root of 4 over 9.8. So if you pull out your calculator and do that, you should get approximately, so remove this space, 0.639 seconds. Okay? Yeah, that seems like a good approximation. Find the time it takes to hit the ground, which is that, and the horizontal distance it travels. Okay, so we know, if you remember from our horizontal motion projectile equations, x final is equal to x initial plus velocity x initial times t. So initial doesn't really matter here, if you recall, because velocity x initial and velocity x final are going to be the same, because it's always going to stay the same, right? X initial velocity doesn't change, and x velocity in general is just the same. It's y because that changes because of gravity. So X final, or you could just subtract both of these to make it delta X, is equal to Vxit. Vxi is 8 meters per second times 0.639 seconds, which should give you around 5.112 meters. All right, pretty solid. Another projectile motion question. A projectile launches at 18 meters per second at 35 degrees above horizontal from level ground. Level ground means we can use the formulas we have stashed. I bet you're just begging to use those, right? Find the time of flight, the range, and the maximum height. So if you remember, t is equal to, which is our time of flight, 2vy initial over g. If it seems a bit abstract to you, I went over the derivation in my video, right? Feel free to check that out. So this 2vy initial. So since it launches at 18 meters per second here, 18 meters per second, the y component of that is going to be 18 times sine 35. Or in other words, 10.324. Okay, so 10.324 meter per second. 2 times 10.324 over g, which is 9.81. So 2 times the answer divided by 9.81. So that should give me approximately 2.105 seconds. That's my time of flight. My range is given by velocity initial squared times sine of 2 theta over g. Velocity initial here is just 18. 18 squared times sine of 35 times 2 is 70 over 9.81, which should give us around 31.036 meters horizontally. The maximum height is given by velocity y initial squared over 2g. Or, in this case, we could just write that as velocity y initial, we know this to be 10.324. So 10.324 squared divided by 2 times 9.81, which is going to be approximately 5.43 meters. This is our maximum height. So yeah, just a bunch of, you just got to know your equations here. If you didn't, it would take you a way longer time because you'd have to use the big five to derive the equations and then use them. This is more free body diagram, so I'm not going to go over it. And here we're going to sketch a motion graph from a description. An object starts at rest, accelerates uniformly to 10 meters per second over 4 seconds, travels at constant velocity for 3 seconds, then decelerates uniformly to rest over 2 seconds. Sketch the velocity time graph on the grid below, then use the area under your graph to find the total distance traveled. Okay, so first let's sketch this part. An object starts at rest and accelerates uniformly to 10 meters per second over 4 seconds. So our object is going to start with velocity of 0 because it starts at rest. At 4, it's going to be at 10. Uniformly means it has a constant slope. Okay, right? Pretty straightforward. Then travels at constant velocity for 3 seconds. So that means it stays at this velocity. It just travels like that for 3 seconds. It doesn't change. Okay, so till 7, it's like that. And then it decelerates uniformly to rest over 2 seconds. So all the way to rest means all the way down here. Uniformly means same again, constant slope. And you have to find the area of this graph under my graph to find the total distance traveled. Because the area under a velocity time graph is displacement, and since the area here is only positive, it's just going to be positive distance, no displacement only, because there's no negative here to change the definitions or warp them to different quantities. So first I'm going to draw different little dividers for each of my shapes. Here I can do 1/2 times 4 seconds, which is the base, times 10 seconds, which is the height. Sorry, 10 meter per second. Seconds cancel out. Left with 20 meters, which is the area under here. Here this is 3 meters, right? And the height again is 10 meters. So the area here is going to be 3 meters times 10 meters. Or sorry, 10 meter per second, 3 seconds again. Keep making the same unit mistake, which should give us 30 meters. Okay? Over here, 1/2 times 9 minus 7. How far is this thing? That's 2 seconds. Times how high is up? Up is this height here. 10 meter per second. Seconds cancel out. 1 times 10, 10 meters. So the total area here under my velocity time graph is 60 meters. That's my distance, and in this case, my displacement as well, but generally not so. A train decelerates from 45 meters per second to rest over a distance of 8-10 meters. Find its deceleration. Okay. So we know that acceleration, we don't know acceleration right now. We're trying to find it, right? So that's the missing variable here. Not the missing variable, it's the one that we need to find. The missing variable is, I believe, time, because we don't have any time here. 45 meters per second is my velocity initial. Rest is my velocity final, which seems to be 0, because rest means 0, right? Distance of 8-10 meters. Delta x is 8-10 meters. So I could probably use the Vf squared is equal to Vi squared, right? Because I see delta x, I see Vf, and I see Vi. The only thing I'm missing is acceleration, which I can find from that. And that equation doesn't include time as well, which we don't have here. That's why we can use this. Vf squared is equal to Vi squared plus 2a delta x. 0 squared is equal to velocity initial squared, 45 meters per second squared, plus 2a, which we're going to find out, we don't know that yet, times 8-10 meters. Okay. So if you subtract the 45 squared from both sides, you can get negative 2025 meters squared per second squared is equal to 2a times 810 meters. You can divide negative 2025 by 2 times 810 meters to get rid of both of these. So I put my units here so I can understand my meters is going to cancel out and give me a meter per second squared. And if I divide this properly, I should get, and we want to keep the negative, right? Because that's what's going to give us our deceleration. Because acceleration is in the opposite direction. If I get a positive value, that means I'm doing something wrong. because deceleration means it's in the opposite direction. So this gives us negative 1.25 meter per second square. Pretty neat value. Box that in. Let's move to the next one. The position time graph below shows a cyclist's position over 10 seconds, including a section where the cyclist is stopped. Identify the time interval during which the cyclist is stopped and find the cyclist's velocity during each moving interval. Okay? So we can understand that over here is probably where it stopped, right? Because he's not moving, first of all. He's staying at the same position. And if you use the velocity definition, which is the slope of this segment, is the velocity over that segment, you can see how the slope is 0, right? So the velocity is also going to be 0, which means he's not moving here. So the stopped segment is this segment. Here's where he stopped. So this velocity here is 0 meter per second. Find the cyclist's velocity during each moving interval. So obviously I don't have the exact position here, but it's approximated to be 3, 9. And then I start at 0, 0. So 9 minus 0 over 3 minus 0. This would be in meters, this would be in seconds. I get 3 meters per second over here. Over here, I start at 6, 9. And I end at, this slope is the same as this. I'm just going to use this point here. 8, 15. 15 minus 9 is 6 meters. Over 8 minus 6 is 2 seconds, which is 3 meters per second yet again. Right, that's it for that one. A soccer ball is kicked at 16 meters per second at 50 degrees above the horizontal. So let me try my best animation of a stick guy kicking a soccer ball. Pretty good, if I do say so myself, right? And then find the initial horizontal velocity and vertical velocity components and the ball's hang time. So his initial force vector over here is 16 meters per second. Angle here is 50 degrees of the horizontal. So the initial horizontal and vertical velocity components. Horizontal component. Okay, first let's see what else they're asking for. The ball's hang time as well. So we want the duration, right, which is t. So we'll do that later, but first let's do this. Horizontal is velocity x is equal to 16 meters per second times cosine of 50. So if I pull out my calculator and do that, that's around 10.28 meters per second. Velocity y is 16 meters per second times sine of 50 degrees. So around, now I type in sine of 50, 12.2, I'll approximate it to sits here, 12.26 meters per second. So those are your components. Okay, and then you want to find the hang time. So if you remember the formula for time, it's 2y, so 2vy initial over g. So this should give you, what is vy initial? Over here you can see that's 12.26 meters per second. So 2 times 12.26 meters per second over 9.81 meters per second squared. This should evaluate, so the units cancel out to bring only seconds. And if I was to simplify this, I get 2.569 seconds. So pretty short duration, all things considered. Yeah, not that long. So now let's move on. Okay. So, an 8 kg sled is pulled across ice by a rope at 30 degrees above the horizontal with 45 newtons of applied force, while friction provides 6 newtons of resistance to the sled's motion. I want the horizontal component of the applied force, the net horizontal force and the resulting acceleration, the normal force the ice exerts on the sled, accounting for the velocity component of the rope's pull, how far the sled travels from rest in 5 seconds, and its velocity at that moment. So this is a lot of stuff, right? And I would say it leans more towards the force section. And this would be a more useful problem for the force video. So I won't cover it right now. I just circled it to make sure that you guys definitely look at this, because this is one of the, it's the hardest, it's a hard problem, and it's pretty representative of what the hardest problems in the test could look like. So I just circled it so you guys make sure you look at it. And if you didn't get it, it's fine, because you want to look at the other videos regarding force to be able to do this. Let's just do some regular kinematics then. The velocity time graph below shows an object's motion over 12 seconds across 4 segments. I want to find the acceleration during each segment, the total displacement, the total distance traveled, the exact time interval during which the object is moving in the negative direction and speeding up. Okay, not just which segment. So let's find this first, the acceleration of during each segment. Segment 1 over here, I would say that's about sits over here, right? The 3 comma sits here, and then 0 comma 0 here. So the slope of this graph would be 2 meters per second squared. Over here we have same thing, 3 comma sits, and 6 comma 2. You subtract, you get negative 4 over 3, so negative 1.333 meters per second squared. And then over here 6 comma 2 again, and then 9 comma negative 5. So it would be negative 7 over 3 meters per second squared. Over here again, 9 comma negative 5, 12 comma round, I would say this is around the between negative 10 and 7.5. So 8 would go there, 8.5. Yeah, I'll approximate this to be 8.5. 12 comma negative 8.5. So then negative 8.5 minus negative 5 should give us negative 2.5. Oh, sorry, negative 3.5 over 3, because 12 minus 9 is 3. And that's just about negative 1.167 meters per second squared. Find the displacement, which would just be, so I could just multiply this area all by itself. I'm not going to do that right now because the units are a bit wonky. So I'll leave it to you if you decide to do it. But this one would have a positive area, and then these two, this would also have a positive area, and then these two would have negatives, and then you'd have to subtract this from the positive displacement to get that. The distance, you just add the magnitudes of both of them. And so D is what I really want to go over. The exact time interval during which the object is both moving in the negative direction and speeding up. So when is it moving in the negative direction as well as speeding up? Negative direction is moving here, right? Going in the backward direction. What does it mean by speeding up? That means the velocity is increasing in magnitude, which it is, right? It's getting to negative 2.5, then it's getting to negative 5, then it's getting to negative 7.5, which means it's going faster and faster in the backwards direction. So from this whole point, not seconds, because that's over here, right? We still have a positive velocity. So from 7 seconds, which is where we start, to very end, 12 seconds. 7 seconds is where we hit 0 and we start going the negative direction, right? Okay, then let's go over 18. A ball is launched from the top of a 38-meter building at 22 meters per second at 40 degrees above the horizontal. So 40 degrees is like that. Find the total time until it lands at street level and the horizontal distance it travels. I wish we could use our time and period and range equations, but it's not level ground, right? So we can't use those. We're just going to have to do this the old way. So we start at 38 meters, okay? So this is my y initial. 22 meters per second is my velocity initial. Theta is 40 degrees. So if I wanted to find out when I hit 0, so I could use this equation. YF is equal to YI plus VIYT plus 1/2 AT squared. Or in this case, you could just write down negative 1/2 GT squared. So YF should be 0 because it hits the ground. YI is 22, or sorry, 38. 22 is the velocity. Velocity I, Y initial. So that's just 22 times sine of 40. Which is 14.14 T minus 1/2 times 9.81 times T squared. And then this you just plug into your calculator, okay? You could either use the quadratic formula, or you could just use a graphing calculator, and you can see where this hits 0, which is what I'm going to do right now. Because usually for tests like these, they allow you to have your graphing calculator. Of course, you could also just solve it using quadratic formula, but it's a bit more easy. Now you're going to get two values, okay? And one of them is going to be a negative value, which you know is not possible, right? Because you can't have a negative time. So you have to look at the other value, which is the positive value, which is around 4.615 seconds. Right, so that's the time where I hit 0, which is fine. Now, the other thing I can do to find out is the horizontal distance it travels, right? That's the other thing I need to find out. So that's just Vx, or x final. Vx is going to be, so Vx is equal to Vi x, and Vx final is the same as Vi x. That's what I was going to write. So if I remove this, x final is equal to x initial plus Vx times t. There's no initial or final needed here because they're both the same. So delta x is equal to Vx times t, or Vx is just going to be 22 times cosine of 40 degrees times, this time over here, 4.615. So this should give us around our units are going to be in meters, so 77.77 or 78 meters. Yeah, 77.78 meters, which is kind of revealed by the graph here, right? Spoiler alert. But yeah, which just means we got the question right. Yeah, so now let's go over one of these questions where we have to have a system of equations. What do I mean by that? Well, why will I spoil the surprise, right? Projectile launched from level ground, so that means we can use our equations. Thank God, right? Reaches a maximum height of 15 meters and lands 96 meters from the launch point. Find the launch angle and the initial speed. So we want to find theta and v initial. Just the magnitude, because initial speed is just the magnitude of v initial. Maximum height is h, capital H, is 15 meters, and 96 meters from the launch point, so delta x, or the range, you could say, is 96 meters. So we could set h to be, we know h is vyi squared over 2g, right? So we know that this is equal to 15 meters. And then we know what else? We know about the range. We know that vi squared times sine of 2 times this angle over g is equal to 96 meters. Okay, that's fine. A bit hectic to solve, but fine nonetheless. And then what we can do is we can change this vyi squared to be vi squared times sine squared of theta. Okay, because vy is just vi sine theta. So if you square that, you get squared on both of these. And then we can also change this to be 2 times 9.81. So you can multiply by this denominator on both sides. So it's going to be equal to 15 times 2 times 9.81. And the units are going to be in meters squared per second squared, because this is, first of all, this is meter per second squared, because that's acceleration due to gravity. And over here, velocity I squared is meter squared per second squared. So 15 times 2 times 9.81 is 294.3. And this is going to be in meters squared per second squared. That's equal to velocity initial squared times sine squared theta. Okay, and then I can take the square root of this, the square root of this, and the square root of this. Velocity initial times sine of theta is equal to, so 17.155 meter per second. But that's not even half there, right? We need to find the launch angle and the initial speed. And we just have nothing here. We just have something we could use, but we have to find a way to use it. Now, over here, velocity initial squared times sine of 2 theta. How can we plug this in? So we know sine of 2 theta. So there's two ways you can use this, right? If you don't know the sine of 2 theta is equal to 2 cos theta times sine of theta, identity, then this might be a bit hard. But if you do know it, it's fine. Otherwise, if you don't know this, then I would recommend just, let's see. You could just use vi squared sine squared theta over here like this. And you could just use that to substitute into this. But don't worry about it, okay? That's a bit too hard. That's not something you'll be given if you don't already know this identity. So vi squared times sine of theta times 2 times cosine theta is equal to 96 times 9.81. What I do is just multiply the g on both sides. It's 96.9.81. So 96 times 9.81, sorry, is 941.76 meters squared per second squared. And this stuff can simplify to, we know velocity initial times sine theta is 17.155 meter per second. So that times 2 times cosine theta times velocity initial, because there's 2 of those, right? So then we could divide by this on both sides. We're left with velocity initial times cosine theta. So let me scroll a bit up so you can see better. Is equal to 27.45 meters. Okay. Now, how do you relate these two equations? You can just divide them by each other, right? So velocity initial times sine theta is 17.155. Velocity initial times cosine theta is 27.45. Divide both these equations by each other. Get tangent of theta is equal to 17.155 divided by 27.45. So you get 0.625. Then you arctangent that. You make sure you're going to be in the right domain, because you realize how. So first, this is 32 degrees, and we know that it goes like this. So we know that it's in the same angle as range as negative pi over 2 and pi over 2, which is the arctan domain. Okay, so 32 degrees is our angle. And then velocity initial, we could just use any of these equations, right? Velocity initial times sine of 32 degrees is equal to 17.155. 17.155 divided by sine 32 is equal, so velocity initial is equal to 32.373 meter per second. So it took a lot of work, and this dividing thing might have been a bit confusing, but other than that, I think it was an alright problem. So this is probably the hardest kind of problem you'll be given. If you know how to do this, you're pretty good. Just remember that you can divide these two to make tangent of theta, okay? This is also goes into the force section. I just wanted to highlight it because I'll be going over it in the force video PDF. Even though I'll have a new PDF, I'll go over these as well. Okay, so let's try this. This one also combines free body diagrams with kinematics. I don't know whether I want to go over it that much. So force, yeah, everything regarding force we'll cover in the next videos. This one also I circled because I wanted to go over it. It does have a lot of kinematics in it, but it contains more FBD and force than I would deem kinematics. So we'll check that later. This one we can do. A ball is thrown straight up from the ground at 25 meters per second. At the exact same instant, a second ball is dropped from rest from a height of 30 meters directly above the launch point. Find the time at which the two balls pass each other and the height above the ground at which that happens. So, I mean, you're kind of given the answers here, right? But if you want to know how to do it, because you won't be given the answers in the test, obviously, then follow along with me. We'll write two parabolic equations for both of them, okay? Using the same yf is equal to yi plus viyt minus 1/2 gt squared. Yf, so yf is going to be, which we don't know, right? We need to find that out. So yf is equal to y initial though. Y initial here, so if I'm writing the equation for this, would be 30 meters plus viyt. Velocity initial y is 0 because it's just dropped, right? Just from the time it's dropped. So it just cancels out to become 0. Minus 1/2 gt squared. Okay, so that's pretty straightforward. Now, since this is for the red equation, because we have two equations here, I'll highlight this one in red. And then I'll write another black equation, but I'll highlight this one in blue for the parabola. So the blue parabola. Just my mouth just stuttering here. YF is still going to be the same point. So YF is equal to Y initial, but here it's 0 meters. Y initial is 0 meters. Plus VIY. So a ball is thrown straight up from the ground at 25 meters per second. So that means it's just thrown, the vertical vector itself is 25 meters per second. So it doesn't have a horizontal vector. 25 meters per second times t minus 1/2 gt squared. And then I'll highlight this one in blue so you can see what I'm talking about. Now you set both these equations equal to each other, okay? Why? Because YF has to be equal to each other for them to meet, right? So you set them equal to each other. So 25t minus 1/2 gt squared is equal to negative 1/2 gt squared plus 30 meters. Subtract, so the 1/2 gt squareds both cancel out. 25t is equal to, so no t squared, just t, is equal to 30 meters. So now you could do t is equal to 30 divided by 25. And you should get, so if I was to complete this, 30 divided by 25 gives me around, divided by 25. So we know this is 25 meters per second. So if you might be wondering why the t and the m don't make sense, but over here I just cancel out units to make it a more concise equation. But you can see how that trips you people up, right? This 25 is meter per second. That's why when you divide this becomes just seconds. So 1.2 seconds. Okay, that's where they meet, which is where I got it, right? Now, how do you find the final one? You just plug this this time into any of these equations because any of them will meet at the same point. So I think I'll plug it into this one. It looks a bit more easy. YF is equal to negative 1/2, 9.81 times t squared, 1.2 squared, plus 30. So this meter per second squared here, and then second squared here. So the units cancel out. Negative 0.5 times 9.81 times 1.2 squared. And then that plus 30. Okay? So that's going to be equal to 22.9368 approximately. And then the rounding error that occurred here was probably because I used 9.81, while the PDF might have used 9.8. When I was designing the questions, I might have used 10 or 9.8. But same thing, right? They're basically the same thing. And units, of course, I'll include my units for meters. All right, now on to problem 23. The previous 23 I removed because the VYI squared wasn't working out because level ground wouldn't make that possible. So now let's look at a different problem which I made. A ball is thrown from a truck moving horizontally at 12 meters per second. Relative to the truck, the ball is thrown at 24 meters per second at 35 degrees above horizontal, in the direction opposite the truck's motion, from a height of 1.5 meters above the ground. We need to find the horizontal and vertical velocity components of the ball's velocity, and then combine them to find the ball's total speed and direction relative to the ground at the instant it leaves the truck. All right, so let's get at it first. So I know that this is 1.5 meters because they just gave me that information. And let's find the ball's total speed and direction. So first, the ball is thrown from this truck, right? So if I was to draw them in different colors, we have two components as always. So pink is the y component and blue is the x component. Okay, so the x component would be velocity x is equal to 24 cosine 35. And then what am I going to do? I'm going to do a negative. So this is 35 degrees. I'm going to do a negative, okay, because it's going left. And I'm going to consider left to be negative direction and right to be positive. So I'm going to make this negative. And if you pull out your calculator and do that, you should get 24 times cosine of 35, negative 19.66 meter per second. Okay, negative 19.66 meter per second. But the thing is, you have to remember, this isn't the only velocity x value. There's another velocity x value that we also need to look out for, right? And what velocity is that? That is the velocity of the truck. Because if the truck has velocity, then any object on the truck is going to have velocity as well. Newton's first law, right? Objects in motion stay in motion. If the truck has velocity, that means the balls on top of the truck have that same velocity. So I have to subtract, or I have to add this, right? Because this velocity is in the positive direction. So Vx, my actual total Vx would be negative 19.66, which is this velocity given by the throw, plus the 12 meter per second given by the truck. Okay? Plus the 12 meter per second given by the truck. So my total velocity x is going to be negative 7.66 meter per second approximately. Okay? Yep, pretty straightforward. Velocity y. So my velocity y, there's no components for the truck that's obstructing that. Velocity y is going to be fairly straightforward then. Velocity y is equal to 24 meter per second times sine of 35 degrees. And since it's going in the positive direction, I'm going to say that that's positive. And I'm not going to give it a negative value or something like I did for that. Because this is the negative x direction, but this is the positive y direction, right? So 24 times the sine of 35, or approximately 13.766 meter per second. So what would my speed be? How do we calculate my speed? Well, that's just the magnitude of the velocity, right? Or in other words, so if you just looked at 24 meter per second and you said that's your speed, that would have been a mistake, right? Because we have this velocity vector as well that we have to add with the x velocity vector. So if you did that, well, now you know how to do better, right? So always grab the opportunity to learn. So velocity total initial is squared is equal to velocity y squared plus velocity x squared. So velocity initials is equal to the positive square root of 13.766 squared plus negative 7.66 squared. And if you were to do that, which I'm going to do right now, 13.766 squared plus negative 7.66 squared, you'll get approximately 15.75 meter per second. And that's going to be your magnitude or your speed, okay? Because the magnitude of velocity, so I'm going to represent this like this so you can see, is the speed, all right? Now, what else do we need? We also need the direction relative to the ground at the instant it leaves the truck. Okay, so then we could just do direction is just arctangent of velocity y, which is 13.766 in the positive direction, over negative 7.66. And if you do that, let's see what angle we get. And remember, this angle might not be your final answer, right? Because arctangent domain is restricted. So this gives you approximately negative 60.91. And if you look at the unit circle, that's over here. But our velocity is where? We need a positive y and a negative x, right? So we're over here. But arctangent's domain is only restricted to these two because it's a function. It can't give you all possible two values. So we have to find this other one by ourselves. And how are we going to do that? We're going to use the same angle we got, negative 60.91. And then we're going to add 180 to that angle. Because that's going to take us, so if I was to draw a zoomed in picture here, if we add 180 to the angle, it's going to take us to the exact opposite vector, which is over here, which is what we want, right? So we're just going to add 180 to find the other angle here. 180 minus 60.91. So approximately 119.09 degrees is what we want, okay? That's our direction from the horizontal ground. Now, that's only one part of the question, though. We also have part B. There is a 9-meter tall tree, 15 meters from release point. So, 15 meters. And this tree is 9 meters. Does the ball clear the tree? Okay, so let's find out, shall we? I'm going to erase this at so I get some more space. And how would I go about doing this? First, I have to find an equation for the y, right? To find whether the y at that point is greater than this. So I have to find the y at the second it is at the tree. Or, I mean, we don't know, but the second it covers 15 meters, right? Because the tree is at 15 meters. So the second the ball covers 15 meters is where I want to see whether it's greater than 9 or lesser than 9. How do I find where the second my ball crosses 15 meters? Well, that's in the x direction. So I'm going to use this equation. xf is equal to xi plus v x t. xi I can say 0. xf is negative 15 meters because this is backwards from the truck, right? In the left direction. And velocity x is also a negative value, which is negative 7.66 meter per second times time, right? So time is just equal to negative 15 divided by negative 7.66, which should give you around 1.95 or 1.96 seconds approximately. Okay, pretty straightforward. And then we know that that's the point that our ball is at the 15-meter mark. But we don't know whether the y is greater than 9 or lesser than 9, which is what we're going to find out. So now I'm going to erase this one over here so I have more space here. So make sure you have that down. Right? Okay. And then, does the ball clear the tree? So we need a y equation. So we could use this one. yf is equal to yi plus velocity initial y times t plus, minus 1/2 gt squared. Velocity means y final. We don't know that, right? We are trying to find out whether y final is greater than 9 or less than 9. So I'm going to leave it like that. Y initial, we do have an initial. We can't cancel out this to be 0. It's going to be 1.5 meters because that's the elevation of the truck. plus velocity initial y, which is 13.7 sits, I believe, yeah. 13.7 sits times t, or 1.9 sits. And then all of that minus 1/2, 9.81, times 1.96 squared. So y final has to be 1.5 meters plus 13.766 meter per second times 1.96 seconds minus 0.5 times 9.81 meter per second squared times 1.96 squared. And this is approximately 9.64 meters. So since the tree is 9 meters, our ball does barely cross it, right? 9.64 meters minus 9 meters. We have a distance of 0.64 meters. And this is greater than 9, so we do, of course, cross the tree. Right? So I hope you had fun with these problems. If you have more questions, then feel free to look at my other units. And regarding the free body and force diagrams that we didn't go over this time, I promise we'll go over that in the force unit. So feel free to look out for that as well. Have a good day, and thank you for listening.